Outlier-Robust multimodal fitting on quantum annealers. In multimodal fitting, the objective is to identify multiple underlying models within a dataset, with each model accurately explaining a subset of the data. This process is particularly challenging because, unlike single model fitting, we need to simultaneously determine which data points belong to which models while fitting those models. This dual task adds a layer of complexity that traditional methods often struggle to manage effectively. The challenge intensifies when outliers are present, which is common in real-world datasets. Outliers are data points that lie beyond the inlier threshold for a given model, making them difficult to accommodate within the fitting process. In summary, multimodal fitting is particularly challenging because it's a bit of a chicken and egg situation. To fit the models correctly, you need to know which data points belong to which model, but to figure that out, you need to know the models first. On top of that, the problem is ill-posed. With specific constraints and prior knowledge, there are more possible solutions, making it difficult to pinpoint the best one. And then there's the combinatorial nature of the task. You have to explore countless potential model combinations, which can quickly become overwhelming. But this is where quantum computing shines. It offers advantages over classical hardware in solving certain combinatorial optimization problems, providing a significant edge in addressing this complexity. Multimodal fitting is useful for a wide range of downstream tasks. It is the backbone of many processes in computer vision and beyond, enabling tasks that rely on accurately identifying and fitting multiple models within complex datasets. This technique is vital for applications like depth estimation, structure from motion, and 3D reconstruction. It's also indispensable in tasks like image stitching, motion segmentation, and augmented reality, where precise model fitting is key to success. The importance of multimodal fitting does not stop there. It underpins many more critical tasks, highlighting its role as a foundational technique in advanced data processing and analysis. Over the years, several approaches have been proposed for robust fitting using quantum computing. The first notable work is quantum robust fitting, which was a pioneering attempt but had limitations, such as being applicable only to single model fitting and lacking practical quantum gate realization. The hybrid quantum classical algorithm for robust fitting marked the first use of quantum annealers for this purpose. While groundbreaking, it required multiple QUBOs to be solved iteratively and was also limited to single model fitting. The QMF approach advanced the field by introducing a multi-model fitting solution using a single-pass QUBO formulation. QMF represents a significant advancement in multimodal fitting, particularly within quantum computing. It employs a set coverage formulation combined with a preference consensus matrix to convert the complex task of fitting multiple models into a quadratic unconstrained binary optimization QUBO problem, perfectly suited for quantum annealing. This method allows QMF to address the entire fitting process in a single pass, significantly boosting efficiency over traditional, iterative approaches. However, one of the main limitations of QMF is the assumption of outlier-free data, which can be a significant drawback in real-world applications. In our proposal, we address the limitations of previous methods by using a maximum coverage formulation to reformulate the problem into a QUBO. In this new formulation, any data points not covered by a model are treated as outliers. We argue that outliers must be addressed within the model fitting process rather than relying on post-processing steps. Simply knowing the correct number of models, denoted as K, is not sufficient for achieving robust fitting. Our approach integrates the handling of outliers directly into the fitting process, making it more robust and effective. Building on R-QuMF, we introduced R-QuMF, a decomposed version that breaks down the multimodal fitting problem into smaller, more manageable subproblems. Each subproblem is then solved using R-QuMF, and the selected models are grouped together for a final R-QuMF pass to provide the final solution. It's important to note that this method is similar to the decomposed version to QMF proposed in the QMF paper. Our experimental pipeline is summarized in the image. We start with a dataset from which geometric models are sampled. These sampled models are used to construct a preference matrix, which captures how well each model fits the data points. This matrix and the dataset are then incorporated into the QUBO formulation of our proposed method. The formulated QUBO is solved using a variety of solvers, including quantum annealers, simulated annealing, and Gurobi, to select the most suitable models. To refine the solution, an assignment problem is solved to maximize point coverage for the selected models. Finally, the performance of the pipeline is evaluated by calculating the misclassification error based on the final set of models. For our experiments, we used both synthetic and real datasets. The synthetic dataset consisted of 30 randomly generated points and 5 ground truth models. We also used the Adelaide RFM dataset for real-world tests, which includes 15 multimodal samples with a minimum outlier percentage of 30% and up to 4 moving objects. In another set of experiments, we used 16 multimodal samples from the same dataset with outlier percentages as high as 70%. These datasets provided a robust testing ground for evaluating our proposed methods. Additionally, we also fit planes on a 3D point cloud with 10,812 points and multiple planes to demonstrate our method is generalized and can be used for other high-level tasks. Our synthetic experiments focused on two key aspects, robustness and scalability. For robustness, we fixed the problem size to 40 sampled models and varied the outlier percentage from 0 to 50% using simulated annealing as a solver. The results clearly showed that our proposed method outperforms all other methods by a significant margin. In terms of scalability, we fixed the outlier percentage at 17% and increased the problem size from 50 to 120 using a quantum annealer as the solver. Our decomposed version demonstrated its ability to handle larger problem sizes effectively. In the context of motion segmentation using the fundamental matrix fitting, our method, as expected, did not outperform the older methods QMF and DQMF in outlier-free scenarios. On contrary, in outlier-prone scenarios, our method significantly outperforms previous methods. Although our proposed robust methods may not outperform older decomposed method DQMF in post-processing, it is important to note that our method does not have access to the true number of models K, unlike other methods. Yet, it still performs comparably. Similarly, for homography fitting, our method does not outperform the previous method in outlier-free scenarios but excels in both outlier-prone and post-processing scenarios. In our plane fitting experiment, we are using our proposed R-QuMF method. The results demonstrate our method's ability to identify distinct planes within the point cloud. As anticipated, the fitting accuracy for cylindrical sections of the building is lower than the planar sections, given that our method is specifically designed to support plane sampling exclusively. This limitation is inherent to the design but effectively highlights our method's strength in detecting planar structures within complex datasets. In conclusion, this work has introduced the first outlier-robust quantum multimodal fitting method, delivering state-of-the-art results compared to currently available quantum methods. Notably, our methods outperform existing techniques by an average of 50% in handling outlier cases for real-world data, showcasing their robustness and practical applicability. Our solution is scalable, leveraging the decomposing strategy from QMF, and includes a decomposed version of our method for added flexibility. This work represents a significant step forward in applying quantum computing to complex real-world problems, and we believe it will pave the way for further innovations in the field. For further information, please refer to our paper. Thank you.